So the question today is whether or not magnets are sticking to coronavirus vaccine injection sites. You've probably seen the videos. They look pretty convincing. But we can use some basic understanding of physics, and let's run a few experiments here in the workshop to see what we can learn. I have here a magnet. This is a rare earth magnet made of neodymium. It's a very strong magnet. Neodymium magnets are 10 to 100 times stronger than your average refrigerator magnet. So most people are showing refrigerator magnets sticking to injection sites. If this magnet sticks, then there's at least a chance a refrigerator magnet could stick. But if this won't do it, then a refrigerator magnet definitely won't do it. Just to show the relative strength of the magnet, if we take this large wrench here, large steel wrench, and I think most people know the steel is made mostly with iron. If we adhere the magnet to the piece of steel, you can see that this magnet will withstand strong deceleration forces and still stay attached. It will not come off, even multiple times the force of gravity. So what we want to try and figure out is whether or not this magnet could stick to somebody's skin if some ferromagnetic material were injected under the skin. And that's what the suspicion or fear is that in the injection, which is only a half of a cc or a half a milliliter of fluid is injected under the skin into the muscle. Now, how much of that fluid could contain some element, some ferromagnetic element, or some other nanoparticle that has magnetic or paramagnetic properties? And just to illustrate, this spot of water on the paper towel, this darker spot here, was from putting a half of a cc of water on the towel. It's an extremely small amount of liquid. The syringe would be pulled down here to this level right there. That's barely enough to wet your palm. But if, let's say if we use this towel here as, to represent skin, it's going to represent our skin. We know the skin is about 8/100ths of an inch thick. So if you fold the towel over twice, 3 times, and check the thickness of it, you see it comes in at about 8/100ths of an inch. So it's about the right thickness. So the question is, if we were to inject something into the muscle, beyond the skin into the muscle, could that material either directly or through some other unknown process cause the body to accumulate iron or some other magnetic element or some other nanoparticle such that that accumulation behind the skin would allow the magnet to pull those particles to the skin such that the magnet could pinch itself could pinch the skin between itself and the particles such that it could withstand the force of gravity and not fall away. So just to do the most simple test here, first of all, let's look at the weight of this magnet. This isn't a very heavy magnet. It comes in at 7 grams. Not that this is an extremely accurate scale, but it's close enough. This small steel washer is too light for this scale to even register. If I put 10 or 12 of them on there, it will register, and I'll do that in a minute. But let's see if we were to have something that was this amount of iron or steel inside the skin, right up against the interior surface of the skin. If it could present enough force to the magnet, or the magnet could pull it strong enough such that it could pinch the skin between itself and the magnet. Now you can see that the steel did respond to the magnetic force. It does move. You can see the steel moving. But when we lift this up, it's not strong enough that actually the magnet will stay attached. We take a much larger piece of steel, like this here, and put it on the scale. It weighs in at 44 grams. If we place this on top of the napkin, representing the inside surface of the skin, and we place it against the magnet, it is strong enough, but not very strong. Strong enough that you can almost cause the magnet to stick. It is more than enough steel. It's just the location of it. We know that the force magnetism imparts to steel is a function of the distance between the steel and the magnet itself. As you get closer to the steel, the force increases. We know that. You can experience that, and everyone kind of has an intuitive sense of that. So what if we were to take a stack of washers? This stack, I think, is 14 washers. Let's make sure we get all 14 of them here. And I'll put them on a scale afterwards, but it comes in at just a little more than the mass of the magnet, a little more than the weight of the magnet. It's about 7 grams, 8 grams. If we can balance this carefully on the napkin without it falling over, and drop it down, make contact with the magnet, it's still not enough mass in that configuration to cause the magnet to attach. However, if we take the same number of washers and we spread them out on the surface of the towel, such that they're connected so they'll maintain magnetic continuity, but they'll get closer to the magnet. Now we can pick up the magnet. It's hard to see with this camera angle, but it's under there. It's not a real strong force, but it's enough to cause the magnet, barely enough to allow the magnet to stay attached. So what we can see by doing this is we're using a magnet stronger than most people are probably using in those videos, although some people may be using that kind of magnet. And you can see the amount of iron in the form of steel that would be required. Let's weigh it. That's coming in at 7 grams. And the magnet's 7 grams. So the two of them, it's about equal mass. So again, this magnet is much stronger than your average refrigerator magnet. So at the very least, whatever the size of the magnet is that you're playing with, you're probably going to have a similar size amount of ferromagnetic material under the skin, very close to the skin, in order to cause the magnet to stick. So it may be happening, but despite what we're seeing on the videos, we have to remember that the laws of physics here are not being suspended. They're still in force. And whatever we're seeing, it's telling you what you're going to have to find under there. You're going to have to find a large amount of ferromagnetic material very close to the surface of the skin. That shouldn't be that mysterious. If somebody investigates that, they'll either find that it's there and should be able to explain the process, or they'll find that it's not there and the magnets aren't sticking. So it's pretty simple. I hope this is helpful.